This video covers the analysis of flanged reinforced concrete beams. As seen in this figure, this beam is a flanged reinforced concrete beam, and we will see how to analyze these reinforced concrete beams. Most of the times in practice, the reinforced concrete beams are cast monolithically with the slabs, meaning the formwork will consist of the slab as well as for the beams, and the concrete is cast together for the slab as well as for the beam. That means the beam do not act as a rectangular beam, but it will act together with the slab as well, giving the flange shape like shown here. In this case, the slab will act together with the beam, as can be seen here. If it is a beam in the middle of the slab, as you can see, this is the flange part, and this is the wave, and the reinforced concrete beam is a flange shape, and which we call it as a T beam in this case. And if it is corner beam, it will be a L beam as well, inverted L beam as well. So we'll look into how to analyze these T sections for the flange beams. Also for the precast beams, sometimes the beam are casted in the T shape or the flange with the flange as well, as can be seen here. Again, this is the flange, and these are the waves. So we'll when we are analyzing the concrete beams, we have to take into account the flange part of the beam as well. Now, depending on which section we are dealing with, the flange section might behave as a flange section, or it might just behave as a normal rectangular section as well. For example, as you can see here, it is a continuous beam, and the slab is cast monolithically with the beam here, so the slab will have a contribution towards the performance of the beam as well. Now, if you take a section at the middle here, AA section, we see that it can behave in two different ways. One, there can be two different cases. First one, section AA, when the equivalent stress block, the compression block in the concrete, falls within the depth of the slab. So in this case, the slab is acting together with the wave, so giving the flange section like a T-beam. Now, looking at the section AA, there can be two different cases. First case, if we draw the stress profile, it can be that the equivalent stress block might be within the depth of the slab, and this is the steel stress, and this is the equivalent stress block, and you can see that the depth of the stress block is within the depth of the slab itself. Now, depth of the slab is TF, and your equivalent stress block is less than TF in this case. And essentially for this kind of beam, your compression block is rectangular shape. Even though it's a T-beam, your compression block is essentially rectangular shape, but when you calculate the volume of this equivalent stress block, you have to multiply it with this B, the width of the whole flange itself, not just the width of the wave, but you have to multiply with the whole width of the wave, width of the flange itself. Now, there can be another scenario where, like shown here, there can be another scenario, as you can see here, when the equivalent stress block falls within the wave. That means it goes below the depth of the slab. This is still the stress taken by the steel. Now, this gamma KUD is, in this case, gamma KUD is greater than the depth of the slab, so that means it goes beyond the depth of the slab, and you can see the compression block is actually T-shape. This is a true T-beam where the equivalent stress block depth of the equivalent stress block goes beyond the depth of the slab. You have, when you take into account the compression block, you have to take this shape into account while calculating volume to find the C, that is compressive force. So compared to the first one where the gamma KUD, so in this case gamma KUD was less than TF, that is the depth of the slab. In this case, gamma KUD is greater than the depth of the slab. Now there can be another scenario when we are looking at the section BB here. In this case, in section AA, we know that the tension is at the bottom, the compression is at the top, right? So the compression block is coming at the top. Now, if we look at the section BB for this continuous beam, we know that there is a negative bending moment here. So that means the tension is at the top and the compression is at the bottom. As you can see, if you draw the bending moment, you know that the tension will be at the top at the middle support and the compression is at the bottom. That means for the section BB, the shape is like this, something like this, because the compression block is at the bottom. This is your compression block. And you can see the compression block is pretty much a rectangular shape here. And the tension is at the top, so you have to take all the steel into account in the slab as well. So you have to take the tension reinforcement at the top. So for the section BB, when there is a negative reinforcement, it is essentially behaving like a rectangular beam again, with the compression block shape as a rectangular shape again. So you don't have to treat it as a T-beam, but it is a flange beam, but it is a rectangular beam, and your compression block is of rectangular shape. Now, when we calculate the when we analyze a flange beam, we have to know how much width of the slab that we have to consider as a part of the beam. So, for example, if we have 3 beams like this, and we are analyzing this particular beam, so we have to see how much width of the slab that has to be taken into account when you are analyzing that particular beam. So the slab nearer to the beam will have more stress, and for example, the center to center distance from here to here is B, and the effective width that you have to take into account is this one. That means this part of the slab will contribute towards the analysis of the beam. So we need to know what is the effective width of the slab that you have to take into account, and that's where the Australian design codes will come to give you the equation to find out what is the width of the slab that you have to take into account as a part of the beam. Now, the Australian design code, if you look into the clause 8.8.2, gives us the equation to find out what is the effective width, or it is denoted as B effective. As you can see, the B effective that has to be taken as a part of the beam from the slab. So, so for the T-beams, Australian design code AS3600 gives B effective as the width of the wave, that is this one. This is the wave in this case, and the width of the wave is BW plus 0.2A. And I'll come back to the A here. And for the L beams, it is taken as B effective equals to the width of the wave plus 0.1A. Here, A denotes the distance between the points of zero bending moments, which may be taken as 0.7 L for continuous beam, and where L is the span of the beam. So for example, if you have a continuous beam like this, it is a continuous beam, so you support here and here, so your bending moment shape, the displacement shape will look something like the beam shape, deformed shape will look like this one. So if you so it means that point of the zero bending moments here and here, this is the A. That means if you are looking at the continuous beam, the distance between the zero bending moments in the beam A can be taken as 0.7 L, where L is the span of the beam itself. So L is the total span of the beam, and A is the distance between the zero bending moment point. So if you draw the bending moment for this continuous beam, wherever the zero distance between the zero bending moment is A, and for the continuous beam, it can be taken as 0.7 times the span of the beam. Now, if it is a simply supported beam, your A zero bending moment is at the support, so A can be taken as equal to the span of the beam itself for the simple supported beam. Now if you plug back these values of A for either continuous beam or single supported beam, you can find out what is the effective width of the slab that has to be taken as a part of the beam when you are dealing with the monolithic structure where slab is cast together with the beam. Now, as we described before, so there can be two different cases when we are dealing with the positive moment flanged beam. So positive moment is a case where your tension is at the bottom and the compression is at the top. So there can be two cases as we described before. One where the equivalent stress block depth falls within the depth of the slab, and the second case is where the equivalent stress block falls below the depth of the slab. That means the T shape of the compression area should be taken into account. So first let's look into the first case scenario where the depth of the compression block, that is gamma KUD, is within the depth of the slab. Now if we look back into here, so we are analyzing this one as a first case where the depth of the equivalent stress block is within the depth of the slab. That's the first case. And in the second case scenario, we'll consider if the equivalent stress block goes beyond the depth of the slab, we have to take this T shape into account. That's we'll consider as case 2. So now let's look into the case 1 first and see how we can analyze that. So for the case 1, we are assuming that the depth of the equivalent stress block, this is gamma KUD, that is denoted by this yellow highlighting, is within the depth of the slab, which is TF. So gamma KUD is less than TF. So in this case, we can proceed exactly like the singly reinforced beam analysis procedure. Only thing is that we have to take into account B effective as the width of that compression block. So let's first assume that, as we did for the singly reinforced rectangular section, we assume that it is a tension failure mode, and we'll check it as we go on. So first we assume that it's a tension failure mode, and equating the forces, C horizontal forces C equals to T. Again, drawing the force profile. This is C compression force in the compression block and the T tension force taken by the steel. So the compression force should be equal to T, and the distance between them is the lever arm Z. So equating C equals to T here, the compression block C is again the same equation like we did before. If you remember, this is your stress block, and this is sigma ST, the stress in the steel, and this is your neutral axis, and the depth of this stress block is gamma KUD, and the width of this block is alpha 2 FC dash. And the three-dimensional, if you look in the three-dimensional, the depth of this is spread over this whole section B effective. So the volume of this equivalent stress block is alpha 2 FC dash and gamma KUD, that gives this area, multiplied by the effective width of the beam of the slab that we have to take into account, that is B effective. So only difference is that instead of using B for the rectangular beam, we are using the B effective that takes into account the whole width of the slab here. The width of the slab that has to be taken into account as a part of the beam, that is B effective. That's the only difference. Now, because we are assuming the tension failure, the tension force is again area of steel multiplied by sigma ST, and sigma ST in this case, because it is already yielding, so we can take it as FSY. So it is FSY, we can take it because we are assuming that steel is already yielding. Now plugging back the values of C and T in this equation, is equal to area of steel multiplied by FSY, that gives us a tension force. Now everything is known in this case, so we can compute what is your neutral axis depth parameter KU. So it is AST So this equation gives us the neutral axis depth parameter for the case when your equivalent stress block depth falls within the depth of the slab. And of course we are here assuming that it is tension failure, so we do have to check that as well. So to check that, we have to see epsilon st is greater than sy or not. Again, to draw the equivalence, the stress block, this is alpha to fc dash, and this is your gamma kud, which is within the depth of the slab. Now to check the strain in steel, we are using the strain compatibility equation, and using these two similar triangles we can find out what is the actual strain in the steel and whether our tension failure assumption is correct or not. So to find out the actual strain in the steel, we still use the strain compatibility equation, which is epsilon cu multiplied by 1 minus ku. You already computed the value of ku, so that gives us epsilon cu, where is 0.003. so you can compute what is the value of epsilon st. If epsilon st is greater than or equal to epsilon sy, we know that it is already yielding and our assumption is correct, and we can proceed to find the bending moment. So if that is correct, then we can find out what is your bending moment capacity. So calculate the nominal bending moment capacity if your assumption is correct. So with that we can, again, for the force profile, this is where your compression force is acting, and this is where your tension force is acting, and this is lever arm Z. So the bending moment capacity mu, nominal bending moment capacity, if you take the moment about the point of action of the compressive force C, it is your tensile force multiplied by your lever arm Z. Tensile force is AST multiplied by FSY, and the lever arm is nothing but effective depth D. In this case, your effective depth is up to the center of the reinforcement as always, and gamma kud by 2. You already know the value of gamma as well and ku, and you can find what is your ultimate moment capacity. This is the case when the depth of the equivalent stress block falls within the depth of the slab. Now the second case scenario is when the depth of the compression block is greater than the depth of the flange height. That means the depth of the slab height. So as you can see here, the equivalent stress block goes beyond the depth of the slab, and it is greater than TF, that is gamma KUD. The equivalent stress block depth is greater than the depth of the slab or the flange TF. So when gamma KUD is greater than TF, we will see how we can find the moment capacity for this section. Now, when gamma KUD is greater than TF, what we do is we separate the compression contribution into two sections. So we will we'll break it down into two parts. One is the overhang C flange, that is the compression force taken by this overhang, and the second one is the compression force taken by the central wave. So we are just breaking down into two parts. One is the flange, the overhang part of the flange, and one is the middle wave part. So we are breaking down, as you can see, this is the compression block for the flange, that is the depth is exactly equal to the depth of the slab here, TF, and the second one is the middle portion, the wave one, and the depth is the depth of the neutral, the equivalent stress block, that is gamma KUD. If you can break down into these two parts, then we can find out the total volume of this T-shaped equivalent stress block. So let's see how we do that. So total compressive force is the compressive force acting on this wave plus the compressive force taken by the flange part, the overhang flange part, that is C flange. So that those are the compressive forces should be equal to the tensile force taken by the steel. So the C wave plus C flange equal to T. Basically, we are dividing the compressive force into two parts, the one taken by the center wave and the second one is taken by the two overhangs on the other side. It is just basically to find out, to make it easier to find the volume of the equivalent stress block. So for the equilibrium, as we said, C wave should plus C flange should be equal to the tensile force T. Now C wave is the volume of the stress block within the wave itself, so that is this one. So we have to find the volume of this equivalent stress block within the wave, that is alpha 2 FC dash, and again the depth of this one is gamma KUD, so gamma KUD, and we have to multiply with the width of the beam, that is width of the wave, that is BW. So if you look into the three-dimensional picture of this T-beam for this case 2, now this is the T-beam in the three-dimensional case. Now we know that your equivalent stress block is below the depth of the slab. It is somewhere this one. So we are breaking down into the two portion. This is the wave portion, and this is the flange overhang flange portion. Now the stress block is also acting on both of the sections. So when we are considering the wave 1, the compression force acting on the wave, we have to consider the width of the wave in this case. So that's where BW is coming. And the second part of this compressive force is the compressive force acting on the overhang flange, and the volume of the equivalent stress block within the overhang flange is this area, alpha 2 FC dash, and the depth of this part is TF, that is the depth of the slab, multiplied by the width of the overhang. So that means this plus this one, isn't it? So that's the width of the overhang we are taking into account when we are calculating the volume for the overhang flange. That width is given as total B effective minus BW. So your total B effective is here. So B effective minus BW will give you the summation of this overhang plus this overhang, and that will give us a total volume of the equivalent stress block acting on the overhang flange. And the tension force we know is area of steel, and again we are assuming it's a tension failure mode. So epsilon st is greater than epsilon sy. Of course we have to check it, but at present we are assuming that it is a tension failure, and T equals to AST and FSY. And usually when we are considering a T-beam, we usually have a tension failure, so it's always safe to start with the tension failure mode. So with that, you can solve for KU. Putting back all this equation into this first equation. So alpha 2 FC dash gamma KU D BW plus alpha 2 FC dash TF B effective minus BW should be equal to AST and FSY. We know all of this thing, so find KU. And once you find KU, you have to check our assumption by check the steel strain and verify epsilon st is greater than epsilon sy. If it is not verified, then you have to go and change it into the compression failure mode like what we did before. So even for the case 2 section, as we can see here, we can easily find the neutral axis depth and check whether our tension assumption is correct or not. And then the second step, once it is verified, is to find out your ultimate moment capacity, and that's again the ultimate moment capacity is same like before, but we have two forces here. So the one force is C flange acting at the center of the TF, and the second one is acting compressive force C wave, which is acting at the center of the compression block there, right, for the wave. So, and this is the tensile force T. So the depth of the C wave is gamma KUD over 2, and the point of action of C planes is TF over 2. Now if you look back into the figure here, you can see the compressive force in the flange is acting at the center of this block, that is TF over 2, and the compressive force in the wave is acting at the center of this block, that is gamma KUD over 2. And that's what exactly it has. C wave is acting at gamma KUD over 2, C flange is acting as TF over 2. Now once we know that, we can find out the moment by taking the moment about the tension force, point of application of tension force, because we have two compression force here. Let's take the point moment about T. So mu equals to C wave, compressive force in the wave, multiplied by this distance, which is nothing but the effective depth. So effective depth is from here to the point of application of T. So D minus gamma KUD over 2 plus C flange multiplied by D minus TF over 2. So D minus TF over 2. So that gives us the nominal moment capacity for case 2, where the depth of the equivalent stress block falls below the depth of the slab. So we broke down into the two compressive forces. One is C wave acting on the wave and C flange acting on the two overhangs, and we can find out the ultimate moment capacity as described here.